Hello. In this experiment, I'm going to do a calorimetry experiment. So calorimetry is a practical technique, an experimental technique used to calculate a value for the enthalpy change of reaction. In the previous video, I'll put a link to that up here. In the previous video, I did a calorimetry experiment to measure the enthalpy change for a displacement reaction between copper sulfate and zinc, and I did that reaction in a polystyrene beaker as an insulator to keep all the heat in there. And that's fine for a reaction which takes place in a solution. However, reactions don't always take place in solution, and I'm going to do an experiment now which is a combustion reaction, and I'm going to measure the enthalpy change of combustion for an alcohol. So the alcohol I'm going to use is butanol, and so I've got the alcohol in a spirit burner, and I'm going to use the heat of that flame when I set it on fire to heat up some water. And I'm going to heat up the water in a tin can, so I'll measure the temperature of the water rather than the temperature of the flame. The first thing I'm going to do is to weigh the spirit burner before the experiment starts, so that I get a value for the mass of the whole spirit burner with the butanol in it. And then I'm going to pour some water, and I've measured out in this 250 centimetre cube measuring cylinder, I've measured out 244 centimetres cubed of water, which I'm just going to pour into this tin can. So I've got 244 grams of water in this can. I've got a little stand with gauze on it. I'm just going to stand the tin can on that, and we'll place the burner underneath it. I'm going to monitor the temperature changes in the water using a temperature probe which is connected to my laptop, so we can record the temperature of the water every minute for this experiment. So I'm just going to pop the temperature probe into the water, record the mass of the spirit burner, so that's coming out at 242.45 grams. Okay, so like the previous experiment, I'm going to measure the temperature of the water for 4 minutes, and then at the 4th minute, I'm going to set fire to the spirit burner, and I'm going to let that burn for about 2 minutes, and we'll record the temperature every minute then until we start to get a constant decrease in temperature. Once I've done that, I'll then reweigh the spirit burner to find out the mass of butanol that was burnt in those 2 minutes. Okay, so just coming up to 4 minutes. So I'll set fire to the spirit burner, and we'll leave that to burn for 2 minutes. Whilst it's burning, I'm going to keep stirring the mixture so that the water can keep at a fairly even temperature, even though all that heat is being put in at the bottom of the tin can. What you may be able to see is that the flame is burning with a yellow coloured flame. So that's indicating that an incomplete combustion reaction is taking place. So that's going to affect our results a little bit. Okay, so I've just extinguished the flame, so that's been burning for 2 minutes, and I'll now just carry on stirring the water for the temperature to reach its maximum, but then also to start decreasing. Okay, so that's collected all the data. So what I'm going to do next is to plot a graph of the data and analyse the experiment in order to get a value for the enthalpy of combustion for butanol. Okay, so here's our results written out. We've got the equation there between butanol and oxygen for that combustion, and then we have our results. This one we took readings all the way up to 15 minutes without a reading there recorded at 4 minutes, which was when I ignited the spirit burner. Okay, so plotting the results onto the graph then, again the temperature axis does not need to go to 0, so I've started the axis at 13, gone up to 21. Our points cover half of the graph paper, certainly in that direction and in that direction. So time in minutes along the x-axis. So I've plotted the points before the spirit burner was lit and drawn a line of best fit through those to the 4th minute, extrapolated to the 4th minute, and again the points after the burner was lit and after it had burnt for 2 minutes, and then that period of time there where the water was slowly cooling. So again, I've extrapolated that line back to the 4th minute to give the maximum temperature rise that we would have got if the water had heated up instantly, but also that burner was burning for a couple of minutes as well, so that will also have an impact on our results. Okay, so to analyse the results of this experiment, we've recorded the volume of water that we used, which was 244 centimetres cubed. I've got my mass values from the spirit burner, so the beginning mass, the final mass, and then the difference, the amount of butanol that was burnt, was 0.96 grams. So in our analysis, the first thing we do is to calculate the quantity of heat that was transferred into the water. That's the surroundings. So the quantity of heat is mc delta T. M is the mass of water. So we had 244 centimetres cubed, which would weigh 244 grams. Specific heat capacity of water, 4.18. Temperature change 6.5 degrees, so that gives us 6,629.48 joules. The moles of butanol that burnt, so number of moles would be mass over the molar mass. The mass of butanol was 0.96. The molar mass of butanol is 74.0, so that gives us 0.01297 moles. So then the enthalpy of combustion would be minus Q, because delta H and Q are opposite, divided by 1,000 to convert Q in joules into delta H in kilojoules, times the number of moles to give kilojoules per mole. So putting the numbers in gives us an answer of minus 511 kilojoules per mole. Now I'm not going to do an apparatus error analysis here, because if we look at the data book value for this reaction, we can see that we should have got minus 2,675.6 kilojoules per mole. That value has come from the Nuffield book of data. The difference between that value and our value is 2,164.6. So that number divided by the accurate value times 100 gives us an 81% error, which is massive. So why has this gone so wrong? Well, there are an awful lot of reasons for this. We noticed that when the butanol was burning, it burnt with a yellow flame, so therefore incomplete combustion is taking place. So incomplete combustion will never release as much energy as complete combustion. Also, some of that heat will have been lost out of the side, it wasn't transferred into the beaker. Some of that heat will have been used to heat up the stand and the tin can as well, and so therefore we haven't accounted for any of that heat loss. And also, because the tin can was not insulated, then heat would have been escaping from the surface and from the sides of the can all the way through the experiment. So huge error in this. And in reality, we would use something called a bomb calorimeter to measure a more accurate value for the enthalpy of combustion. So this experiment has shown you how you can measure a value for the enthalpy of combustion for a flammable liquid using a calorimetry experiment.